All right, 2.5, evaluating limits algebraically. So this lesson is going to seem very basic, very simple, especially when we're looking at a continuous function. So a limit of a function equals the value of the function when the function is continuous at that moment. So that means direct substitution is going to give us the answer in these cases. So we can always take -1 and replace all of the x's in it and solve. And as long as there's no domain restriction, we wouldn't have to worry about whether this is continuous or not at this point. So I'm going to evaluate 3 times -1 to the 4th power minus 2 times -1 to the 3rd power plus 4 times -1. All right, so we get a +3, we get a +2, and -4. So the answer is 1. So the limit and the function value as x approaches -1 are both 1. Sometimes direct substitution does not work, which implies that the function is not continuous at that given x value. There is some sort of a domain restriction, but sometimes we can manipulate algebraically and still come up with an answer. Okay, still have a numerical result. And this is a scenario like that. So if I were to do direct substitution immediately and put 4 in, I would get 0 in the denominator. Okay. For that matter, I get 0 in the numerator as well. Okay, so this is currently undefined. However, if I'm getting 0 in the top and the bottom, it's a guarantee that that corresponding factor that's causing the 0 must also be in the numerator. Like I can clearly see it on the bottom. We just have to find it on the top. So we factor when possible. We remove the factor x minus 4, and we are left with a reduced function that is now appears to be continuous at 4, and I would get an output of 8, a limit of 8. Graphically speaking, this function would appear to be a line with a y-intercept of 4 and a slope of 1, but at 4, there is a hole. Right? The limit exists, the limit is 8, but the function does not exist. We were able to manipulate this and come up with a limit, but there still is a hole at x equals 4. So here's a really important concept. We're going to see this quite a bit. We say that f of x has an indeterminate form, or is indeterminate, at x equals c, if the formula for f of c yields an undefined expression of one of the following types. 0 over 0, that's what we just saw. Infinite over infinite, infinite times 0, infinite minus infinite. So indeterminate, right, cannot be determined, aka I don't know, right? It could be this, it could be that. 0 over 0, I could say to myself logically, well, that's 1 because it's the same number top and bottom. Or that's 0 maybe, or that's undefined. Like, I can't come up with a singular answer. Same concept with infinity over infinity. Is it 1? Is it infinity? What is it? Etc. So all of these are forms where I'm not sure. You would say that to yourself. But if a function is indeterminate, then we can transform it algebraically to a function that is defined at the given x value and then be able to evaluate that limit. So essentially, we can manipulate it, right? We can find an answer. But I really want to make an important note at this point. Some number other than 0 over 0 is not indeterminate. This is already established as something that is undefined. Another number besides 0 over 0 is undefined. Okay, so let's take a look at this one. You always want to just do direct substitution, at least a quick mental check right away to determine, are we just going to get an answer? So if I put 3 in, 3 squared minus 4 times 3 plus 3. 3 squared plus 3 minus 12. So we're going to have what? 9 minus 12 is negative 3 plus 3, that's a 0. 9 plus 3 is 12 minus 12. So we have a 0 over 0. We have an indeterminate. It's a guaranteed scenario where I can manipulate this and solve it. So almost always if it's a polynomial, you're looking to factor and cancel it. If I'm getting an output of 0, when 3 gets inputted, that implies that there must be a factor of x minus 3 top and bottom. Now in a case like this where a is 1, factoring is pretty simple. Sometimes factoring is not that simple. Use that knowledge, right? Go into this knowing x minus 3 has to be there. That is what's causing this 0 over a 0. Then you can just think about, well, what's the other factor? So up top, in order to get a positive 3 as my c, the other factor must be a minus 1. At the bottom, in order to get a negative 12, my other factor must be a plus 4. I can double check to make sure that those values add up to the b term, and they do. Negative 3 plus negative 1 is negative 4, and negative 3 plus 4 is positive 1. So they would FOIL back out and get correct. So the x minus 3 is gone. I input 3, and I have 2 over 7. So that implies that this graph, if I put it into the graphing calculator right now, it is a rational function still, right? It doesn't fully simplify to linear, but there is a removable discontinuity. We're going to learn about that soon, but there's a hole at x equals 3. The function is not defined, but the limit exists. The behavior of the graph trends towards 2/7. All right, pause my video for a minute. Go ahead and try these on your own. Okay, you're just factoring, canceling out, and getting a final answer. Okay. I'll give you a hint. They're all indeterminate to start, so you want to cancel. And I'm just going to quickly solve them silently for you. Okay, so you should have arrived at 5, 128, and 1/6. Again, pause this, follow my factoring, but these are all just factor and cancel. Okay, there's definitely other types of indeterminate forms. Okay, so before we saw polynomials or rationals, factor cancel. Here, when you have a radical, right, we're going to always use conjugate. Okay, but the issue, we're not rationalizing a denominator per se. So you're multiplying the conjugate wherever that radical is. The other way to think about it, if I look at this limit as x approaches 4, x minus 4 is that nice, easy factor that I want to have, because that's what clearly cancels the 4 minus 4 out. Yeah, sure, root x minus 2, that also cancels it out, or gives us a 0. But I don't want to work with radicals. So wherever that conjugate is that's causing the 0, or wherever that radical is that's causing the 0, that's the one that we're going to use the conjugate for in order to cancel it out or rationalize it. But it's not always rationalizing the denominator. Okay, so this case, I'm going to multiply by root x plus 2 over root x plus 2, right? When we choose conjugates, we're just changing that middle sign. That way, when we FOIL, the outers and the inners cancel, and we are just left with the first and the lasts. So root x times root x is going to give us an x. You get the positive root 2x, the negative root 2x, and then the minus 4. And that's exactly what we needed. Do not FOIL where the conjugates are not. That would just give you a mess. And again, we want to cancel out that x minus 4. So therefore, we don't want to FOIL and lose it. Cancel, and then evaluate. So we get a 1 over 4. Right? Root 4 plus 2. Okay? Same idea here. Right? The radical is in the denominator. The nice, easy factor that we want is h minus 5. That causes a 0 very nicely. We want to keep it and find it in the denominator. So root h plus 4 plus 3. Okay. Do not FOIL the numerator. Do FOIL the denominator, so your first, the radicals will cancel and you'll have h plus 4. Your inner and your outers will cancel out, right? They're opposites, and your lasts will be a minus 9. So h plus 4 minus 9 simplifies to h minus 5. So that's what cancels. We're left with the numerator being root h plus 4 plus 3. Evaluate with 5 plugged in. So you have 6. Okay, then we have trig. All right, so you've seen rationals, you've seen radicals, now trig. So trig, most common, you're going to manipulate by changing tan, sine, secants, etc. Not sines, I'm sorry, tans, cotans, secants, cosecants, back to sines and cosines and such, and look to see if things cancel themselves out. Okay, so pi over 2 evaluated with tangent, tangent being sine over cosine. Okay, just a quick refresher. Pi over 2 is right up here. That ordered pair would be 0, 1. Cosine, sine. Right, so right now I'm a 1 over a 0. That's not allowed. And secant is 1 over cos, which is also a 0. So I do have a 0 over 0, which is not allowed. So I am going to rewrite this as sine over cosine all over 1 over cosine. Think of dividing by a fraction is like multiplying by a reciprocal. So I can rewrite this again to see it like that, right? Now our cosines, that 0 over 0 is canceling out. And now we're left with sine x over 1, and sine at pi over 2 equals 1. So undefined, but limit exists. Okay. Two rational expressions. Combine them, figure out if you're indeterminate, then manipulate and cancel. So, common denominator, right? So that first fraction needs the x plus 1. Now we have the limit as x approaches 1 of x plus 1 minus 2 divided by the common denominator of x plus 1 times x minus 1. Simplify the numerator. Sometimes these really simple steps we miss, and we're like, oh, nothing cancels, right? But x plus 1 minus 2, simplify it, is x minus 1. Now we remove that factor, and our answer is 1 over 2, 1/2. Okay, one more example. I want to point out that example where something can be infinite but not indeterminate, right? So remember how I said 0 over 0 is indeterminate, but another number over 0 is not indeterminate. It's undefined. So before I begin factoring, I do want to do that quick mental check. If I plug 2 in, I have 2 squared minus 2 plus 5 over 2 minus 2. Well, 4 minus 2 is 2. That's 7 over 0. Nope, that's not 7 over... Yeah, it is. 7 over 0. So any number over 0 equals undefined. Okay, therefore I can't manipulate it, right? There still is a discontinuity. It's just not the same as the ones that we were seeing before. It's not a whole. In this case, it's an infinite discontinuity. There is a vertical asymptote at 2. Okay, so if I were to go to the graphing calculator to get the exact graph, I would have a vertical asymptote here at 2. I have a slant asymptote. I know I'm doing a rough sketch here, so forgive me for that. But it's somewhere's in there. And then the branches look something along these lines, right? So we could do one-sided limits on a problem like this, right? We could figure out left limit. That's going to negative infinity. Right limit. That's going to positive infinity. And that's something that we will do probably in class because it's a good thing to walk through. But that would be something where we just have to figure out the sign. We know that the function exists there. We know that it's growing really large or really small. So is it positive or is it negative? And we'll look at that more closely in class. A couple closing questions to consider. Ignore the homework like always. When does direct substitution not work? So that's when we're looking at our indeterminate forms. And how can algebra help us to find the limit of a function when direct substitution is not an option? So can you factor and cancel? Can you multiply by conjugates? Can you manipulate with trig? Those were the 3 types that we saw today. Okay, nice work. See you soon.